Hiya, welcome to week 6 of this course. So this is the last week you'll have me. So hopefully it's been a fun ride, even with the ups and downs. So today we're going to start off with, or in this video, we're going to start off with what's called vector fields. And this is basically the key object in vector calculus. As you can imagine, this means we're going to be doing derivatives and integration and all that fun jazz. So hopefully you remember all that. If not, remember that you can always come ask questions whenever you want. So first, we're going to define one of the main objects, and this is what's called a vector field. So a vector field W on AN, so this is an affine space here. So remember that AN, this is affine space, and here we have n real valued functions, so n functions on the space. And basically how we define this is we have a set of values, x1 through xn, and basically we just evaluate them at each of these functions. So h of h1 of x1 to xn times the vector e1 all the way up to hn of x1, xn of en. So basically this is assigning to each point. So a point here you can view as, right, xn. So this is a point in affine space. And we're going to associate it to a tangent vector, right? So this is our vector here, right, vector. W of p. So W of p, this is our p here. And this is basically giving us a vector in the tangent space. So remember, the tangent space basically takes a point and it looks at all the vectors that kind of come out of this space. So as a very simple, quick and easy example, as you can see above, W is a vector, or else a function, but it produces a vector. So W gives us a vector. So in particular, if I give, as an example, if I want to have a function on xy, well, this is going to give me a function ex plus ey. This is a perfectly valid vector field. So you just plug in any point. So 1, 2, for example, will give you some point, and that'll give you the vector field. So here, these h1s and hns, so the things we have up here, right? So here are real valued functions from here. These can be seen as h1 is equal to x and h2 is equal to y. And here we've mentioned that this you can see in figure 4. So let me zoom forward a little bit so we can see what figure 4 looks like. So here's figure 4. And here on the left hand side, this is our vector field, xex plus yey. And so you can kind of see at every point the vector is going to look a little bit different. In essence, every point is different. So at every point we have some vector. So here you don't really want to think of this as like there's gaps in between. Every single like thing in between here has some vector coming out of it. This just allows us to kind of see what's happening. So in this case, it kind of looks like everything is expanding outwards. So let's look at, so that's the basic definition. And the thing is, what we're going to want to do is look at vector fields that are in some sense nice. So in order to do this, the first thing we're going to define is a gradient. So a gradient of a function you should have seen before, or a vector field in particular. So the gradient of a function f, this is going to be the partial derivatives. So here, this is what I was saying. If you don't remember partial derivatives, you'll come and ask because you don't want to be left behind. The f of dxn en. And so basically what we have is we want f to be some smooth function. We haven't really said what smooth is. We'll let that, or no, we talked about this last time. Yeah. So smooth function is basically, remember that everything has its partial derivatives. And so because there's partial derivatives, we can define this in this way. And so this gives us a particular vector field, right? So remember that a vector field is a function, and in particular, our vector field, we're going to denote by delta nabla of f. So this little symbol here, if you haven't heard it before, this is called a nabla. Or sometimes I'll just say upside down triangle because it literally looks like an upside down triangle. And what we're going to say is that if a vector field is coming from the gradient of some function f, then we're going to call it a conservative vector field. What this is basically saying is that if a vector field w, right, so this here, let me choose a different color. If this vector field w arises as gradient of some function f, what this is saying, in other words, that conservative is saying w is equal to nabla f for some f. We don't know what it is, but it's some f. This is what conservative basically means. So let's look at some examples of this. Yeah, no, actually, so we'll stop here. And in the next video, we'll look at examples of this and also talk about directional derivatives. So I will stop here. Oh, wait, no. Yeah, I will stop here. And I will see you in the next video. Peace.